All right, and this example 3, we're going to be talking about some new vocabulary terms and kind of reviewing the ones that we've already talked about in example 1 and 2. So let's go ahead and remember. We talked about special systems. The first was the one that we're most familiar with for lessons 1, solving systems by graphing. Number 2 with solving them through substitution, and lesson 3, which was solving systems of equations by elimination. For the most part, we were dealing with 2 lines that had one intersection, which was a point, right? So earlier in this lesson, we said that those are systems that have at least one solution are called consistent, okay? So we said that if they have one solution, that is a consistent system. Then the second example was when we have 2 lines that are parallel and they don't have a solution, and then we said that those were inconsistent systems, okay? Parallel lines which have the same slope, different y-intercepts. All right, and then we talked about a third type, right? And that third type was if you have the same line which has the same slope and same y-intercept, then you have an infinite amount of solutions, but we didn't really put a vocabulary term on that, right? So let's go ahead and read this next thing. What it says is consistent systems. So remember, so far what we've talked about when it comes to consistent is 2 lines with one intersection. That is a consistent system, right? So we know that we're talking about that. So let's go ahead and read on. Consistent systems can either be independent or dependent. Okay, so that means that the consistent systems really branches off into 2 categories. You have independent or dependent. So we have consistent, and that, did I spell that? No, I'm missing an S. Consistent branches off into 2, independent and dependent, right? So this is new. This part is new. So what makes it an independent versus a dependent system? Well, an independent system has exactly one solution. So the graph of an independent system consists of 2 intersecting lines. So here, with one solution, 2 lines, there's one intersection, so we can say that this is an independent solution, or independent system. Independent system. So it's a consistent independent system. All right, you get another little loop-de-loop, okay? Okay, so that means independent system is just 2 intersecting lines, right? There's one solution. Okay, so now we know what an independent, what is a dependent system? A dependent system has infinitely many solutions. The graph of a dependent system consists of 2 coincident lines. So that means a dependent has 2 lines that are right on top of each other, which is really our third right here. So this was actually a consistent dependent, maybe I should say dependent consistent or consistent dependent. Oh, that's okay. Consistent dependent system. All right. Perfect. So now we know the difference between an independent and dependent. So there's 2 types for consistent. And then right here, this just has it all, right? So in the next couple of examples 3, you're going to be doing what's called classifying the systems of linear equations. So whenever you have intersecting lines like this that has one solution, you're going to call that consistent and independent. Okay, that would be the classification. Whenever you have coincident lines, which are 2 lines which are the same, right? That's going to be consistent and dependent. That is the classification. And then lastly, when you have 2 parallel lines, like we've discussed before, that is inconsistent. So there's no solutions, you know, all of this stuff we have previously talked about. So consistent and independent, right? There's only one solution and they have different slopes, just intersecting lines. Whenever you have a consistent and dependent system, those are coincident lines, which means you have two lines which are the same. So there's an infinite amount of solutions and they have the same slope and the same y-intercept. And then lastly, when you have something that's inconsistent, that means the lines are parallel, there are no solutions. So the answer is no solution. And then they have the same slope and different y-intercepts because you're dealing with parallel lines. So yeah, so this, you can refer back to this table, but you really need to commit this information to memory, especially the classifications, consistent and independent, consistent and dependent, and then finally inconsistent. All right, let's go ahead and get started and look at a few problems and see how we're going to apply this knowledge. So first, we're just going to look at example 3.8, and we're just classifying the systems of linear equations. So we're just going to classify this system. You know, I think what I'm going to do is just solve this algebraically. I think that that's kind of the easiest way to do that. So I'm going to take this first equation. Actually, let's take this one here because it has a regular y, okay? And we're just going to solve it for y. So we have negative 1/3 x plus y equals 1. And I'm going to get y by itself, so I'm going to add 1/3 x to both sides, which means I'm left with this, okay? So, all right, what is this? This is my equation 1, this is my equation 2. Okay, so this is my equation 2 answer, so that means I'm going to take that and substitute it back into equation 1, right? So I'm going to write equation 1, 3y equals x plus 3. And just take this information, substitute it in for y here. And notice because there's that 3 in front of y, I have to substitute it in parentheses. So it's going to be 3 multiplied by the quantity, substituting that in, equals x plus 3. Okay, now I'm just going to multiply both of these things. 3 times 1/3 x plus 3 times 1 is 3. Okay, now here I'm multiplying fractions. I'm going to take that 3 and make it a fraction. And then I'm going to look to cross cancel. These have a common factor of 3. 3 goes into 3 one time, 3 goes into 3 one time. I multiply across. That all ends up just being 1 times x, which is x, plus 3 equals x plus 3. I have variables on both sides, so I want to try to get the variables on the same side. So since they're the same, it doesn't really matter. I'm just going to do the inverse operation. And here we go. They both cancel out, which is totally fine. And we're left with 3 equals 3, which is a true statement, which means that our answer is infinite solutions, right? Okay, so so we have to classify the system and give the number of solutions. So I'm just going to go up here. And if you remember, when we have infinite solutions, that means we have coinciding lines. We have the same line. So that is the consistent and dependent. That is the classification. So this is a consistent, dependent system with, so it says classify, that's a consistent dependent system, that's the classification, and then with the number of solutions with infinite amount of solutions. So that's how you'd answer it. There you solve. All right, perfect, perfect. Let's go ahead and move on to 3B. So 3B says classify the system, give the number of solutions. So for this one, I kind of see, I'm just going to solve it algebraically again. I see that this is already solved for x, but it's not totally by itself because there's this negative here. So I can either multiply the whole thing by a negative or just move one of them up here. I think I'll just move one up from up here over. I think sorry for shaking this, I accidentally hit it. I think that will be easier. So I'm going to take this and I think I'm just going to solve for y. So x plus y equals 5. I mean, I could solve it for x, but then I'd have to substitute it in with a negative, and it's probably going to be easier just to substitute it into this y where there's nothing. So I think it's easiest to solve for y and then substitute it in here. I just feel like that's going to be the simplest. Okay, so I'm getting y by itself. So yeah, when I solve these, I try to tell you like the strategy, what I'm looking at, what I'm thinking, just because I've done these for a long time and a lot of years, and you just kind of pick up different things along the way. So I'm just sharing that knowledge with you. There's obviously other ways to solve this where you'll still get the same answer. But sometimes, like the strategy or the things that I say, it will just kind of make the problem easier and simpler. So I'm just trying to pass that like torch on to all of you, trying to make your life a little easier. So we have this, and what is this? This is equation 1, right? We just solved equation 1. So whenever you do this, this is equation 1. So now we need to substitute it into equation 2. Which is right here. Okay, so this is what y equals. So I'm just going to substitute it in. And since it's that positive 1, we don't need to put parentheses. So it's really just 4 plus, substitute that whole thing in, 5 minus x equals negative x. Okay, we have variables on two sides of the equation. So I want to try to get them on the same side. Usually move the smaller, but they're the same, so it doesn't matter. I'm just going to use the inverse operation, which would be to add x to both sides. Cancels here, totally okay. That's not a problem. Remember, whenever the variables cancel out, that means we're either dealing with infinite solutions or no solutions, dealing on the statement that we're going to get next. So 4 plus 5, that's 9. And then negative x plus x is 0. Don't be afraid to write 0. When it cancels out, it means there's nothing there, and so nothing represents something. It's 0. So what we have here is this a true statement or a false statement? It's a false statement, which means there's no solution, right? But what do we have to do? We have to classify the system. So I'm going to go back here. And remember, when we have no solution, that means we're dealing with parallel lines, right? So the classification is that this is an inconsistent system. So write our answer here. Inconsistent system. And then the number of solutions are no solutions. There's none. So that is how we would express our answer and how we would show all of our work. All right. Let's go ahead and move on to the next one, 3C. So 3C says, classify the system, give the number of equations. All right, great. So again, we're just going to solve these algebraically. This is nice. This one's already solved for y, so I think we can just directly substitute this in for y, and then we're good to go. So what I see here is I'm just going to substitute it straight in. There's a 1 there, so I don't need to put it in parentheses. So I'm just going to write this and directly write it right there. So 4 multiplied by x plus 1 minus 3 equals x. Okay, then we distribute the 4 to both. So 4 times x is 4x. 4 times a positive 1 is a positive 4. Okay, so now we have x's on both sides. So I always say, let's move the smaller, but here x is already isolated on this side of the equation, and there's a whole lot of stuff going on over here on this side of the equation. So this is one of the few examples where I move the bigger one just for fewer steps. So the inverse of a positive 4x is a negative 4x to both sides. This cancels. 4 minus 3 is 1. X minus 4x would be a negative 3x. And then we just get x by itself, divide both sides by -3. And so that leaves us with 1 over x. And I'm going to use that symmetric property of equality and flip it because it means the same thing. So now we have what x equals. So the x's didn't cancel out, right? Whenever those x's cancel out, we know that we're dealing with infinite solutions or no solutions. But in this example, the x's didn't cancel out. So we know that we're not dealing with infinite or no solutions. We know that we're dealing with a consistent and independent system. So we actually have to figure out, right, what that point of intersection is. So this is going to be one solution. So let's go ahead and figure that out. And it's in the ordered pair. So we know that we found the x, but we have to find the y. So let's go ahead and we can substitute it into this equation. It's already solved for y. So maybe I'll do a different color. Maybe I will put it up here just so I have lots of room. Okay. So I'm going to write that original equation again. Right? And then substitute it -1/3 for x. Okay, so order of operations says I have to do parentheses first. This is a fraction, so I'd be adding, so I really need to make this 1 into a fraction. Super easy, it's just 1 over 1 is the same thing as 1. And then whenever you're adding fractions, remember you need a common denominator, right? So I'm going to get that common denominator between 1 and 3 would be 3. So I'm going to multiply the bottom and the top by 3. Okay, what I'm left with is -1/3 plus 3 over 3. Okay, then combine like terms. And I get -1 plus 3 would be 2/3. And now I am, multiplying fractions. So I'm going to make this a 4 over 1. Remember, whenever you're multiplying fractions, first you look to cross cancel, and then you just multiply across. So I don't think there's anything we can cancel out, so multiply across. 4 times 2 is 8. 1 times 3 is 3. So the answer is 8/3. So that means our solution is -1/3, 8/3. And so that is one solution. So it says classify the system, give the number of solutions. So this is a, right, intersecting line, so that classification is going to be that it's consistent and independent, and it has one solution, and we discovered the solution. So we're going to say, I'm going to move this right here. This is a consistent and independent system with one solution, and the solution is -1/3, 8 over 3. And there you have it. Perfect. Okay. We went over 3 different examples, right? One was when the variables canceled out and we were left with a true statement. So we knew that that was infinite solutions, which meant that the classification for that was that it was a consistent dependent system and it had infinite solutions. And then we found another one with this second example where the variables canceled out again, but we were left with a false statement, which meant no solution. So that was an inconsistent system with no solutions. And then finally, we just discovered a problem where the variables stayed, nothing canceled out. So that meant that we found the x and then we found the y, which meant there was one solution, right? Where those 2 lines intersected, and then the solution was -1/3, 8/3. And so that was a consistent and independent system with one solution being that right there. So now it is time for you to go ahead and check it out. I want you guys to try this one on your own. So go ahead, you're going to classify the system, give the number of solutions. So go ahead, pause your device, work that out. When you get done, press play, and we will go over the answers together. All right, we're back. Let's go ahead and see how you did. So for this one, I'm going to solve it algebraically. It's already solved for x, so I'm just going to substitute that in here. What's nice is that's positive, so I don't need to write any parentheses. I can just write this directly right there. So I'm going to go ahead and get started. Negative 2y plus 2, substituting that in for x, plus 2y equals negative 4. Now let's just go ahead and solve. So first we have to distribute the negative 2 to both things. So negative 2 times y is negative 2y. Negative 2 times a positive 2 is going to be negative 4, plus 2y equals negative 4. What's nice is these two y's, they cancel. So whenever those variables cancel out, you know you're dealing with either infinite solutions or no solutions, depending on what this statement is. And we're left with negative 4 equaling negative 4. This is a true statement, which means infinite solutions, right? So this is a, whoops, sorry, I hit it. So this is a consistent dependent system that has infinite solutions. So infinite solutions means they're, these two lines are actually end up being the same line. So they're coinciding lines. All right. There we go, there we go. Okay, let's look at the next one. Okay, we have 3b. So let's go ahead. It's your turn. I want you to try to do 3b. Check it out, 3b, and also check it out, 3c. So where's my friend? Here's my friend, the pause dragon. Remind you to pause. Go ahead and work those problems out. When you get done, press play and we'll talk it over. All right, see you in a bit. All right, we're back. Let's see how you did. So this is nice. I really like this one. So classify the system, give the number of solutions. We can do that. These are both solved for y, so let's just go ahead and set them equal to each other through substitution. I like this one. This one's kind of nice and friendly. Okay. Got to do the distributive property here. Negative 2 times negative 1 is a positive 2. Okay, have variables on the same side. I'm going to move the smaller one. Negative 2x is smaller than negative x, so I'm going to do the opposite of a negative 2x, which would be adding 2x to both sides. That one cancels. I'm left with 2 equals negative x plus 2x is just a positive x. And then I'm just trying to get x by itself, and 2 minus 3 is negative 1, so it ends. Looks like we end up with x equaling negative 1. And since those variables didn't cancel out, right, we know that we're dealing with intersecting lines that are going to have one solution. So let's go ahead and figure out what that y part is. I'm going to write this equation here and stick in negative 1 here. Now there's a negative in front of that x, so make sure you use parentheses, right, when you stick that in. And we have a negative and a negative, which is a positive. 1 plus 3 is just 4. Okay? So there we have it. We have one solution. So this is going to be a consistent and independent. Consistent and independent system. That's the classification. It has one solution, and the solution is negative 1, 4. So there you have it. Our classification, number of solutions, and there it is. So if you got that one right, awesome, awesome. Let's go ahead and look at the next one here. This is our last one. This is 2 over 3. Okay, so this is like this. I'm sorry I didn't see that before, but it should be that. Okay, so go ahead and write that line in. I hope that didn't confuse anybody. So this is nice because this is already solved for y, so I'm just going to go ahead and substitute this 2/3 x directly in here for y. Now notice that there is a negative 3 in front of this y, so we have to make sure that we put that in parentheses. So let's go ahead and do that. So I'm going to write the 2x first. So 2x minus 3, and then I'm going to substitute this in for y, so I need parentheses. 2 over 3x equals 6. Okay, so we have to simplify. We have to simplify this first. So this is basically just multiplying fractions. So I'm going to make this -3 and -3 over 1. And whenever you're multiplying fractions, you have to look to cross cancel first. So here, you can see that there's a common factor of 3. 3 goes into 3 one time, 3 goes into 3 one time, and then we would just multiply across. So I'm going to rewrite this 2x. And then basically this is -1 times 2x, which would end up being a -2x. All over 1 times 1, which is just 1, so I don't need to write this -2x over 1. -2x over 1 is just the same thing as -2x, so I'm just going to keep it like that. Equals 6. And then we simplify. 2x minus 2x is just 0. They cancel each other out, and when that happens, that equals 0. It equals nothing, and nothing is represented by the number 0. So don't be afraid to write 0. Sometimes people are afraid to write 0, but that's okay. Now, the variables canceled out. That's totally okay. When that happens, it's either going to be no solution or infinite solutions, depending on what this statement is. And this is actually a false statement, which means it's no solution. So then we just need to classify, right? So we're going to classify this as an inconsistent system. And then the number of solutions are no solutions. So that is it. So if you got that one right, you did a wonderful job, and we will see you back with for example 4.